Hi, this is the next video on the Year 1 and 2 combined probability. So in this video we're going to look at tree diagrams again, this time focusing on conditional probability. So in the last video we talked about the formulae that we can use for conditional probability. So if given that something's happened, what's the probability of something else happening? So the focus is going to be this time on conditional probability, but to do with trees. There may be an element where we might dip into a Venn diagram or the formulae, but definitely the main part is, or at least the starting point, is going to be from a tree diagram. So I've just got two tree diagrams here. Okay, you know how tree diagrams work. So each branch, or each set of branches has got to add up to 1. That's showing something happening and something not happening in this case. Okay, and then something else is happening. Now this one is showing independence, so you can think of this as being something is being replaced. That's the usual scenario. This one is showing dependency. So this is saying that whatever the probability of this is, it's dependent on the fact that this has happened. So this will be an example of notation for something that isn't replaced. So you've got probability of A, probability of not A, the probability that B occurs given that A has already occurred. So that is showing that that is dependent on that. And then the probability that B doesn't occur given that A has occurred, and so on. Okay, so these ones here, these branches are dependent on these branches here. Okay, so nothing new in terms of how to work out the diagrams, but the notation is new, and you should be able to now use the formulae in conjunction with a tree diagram for more complex problems if you need to. So we're going to have a look at a few examples that just get progressively more complicated, I guess. So the first one, the turnout of spectators at a motor rally is dependent upon the weather. On a rainy day, the probability of a big turnout is 0.4, but if it doesn't rain, the probability of a big turnout increases to 0.9. The weather forecast gives a probability of 0.75 that it will rain on the day of the race. Okay, so if we draw a tree diagram to represent this information, so it's dependent on the weather, so the rain has to come first. So it's either got to rain or it's not going to rain. And we're told that the probability that it will rain is 0.75. So on there it's going to be 0.75, which means that must be 0.25. On a rainy day, the probability of a big turnout is 0.4. So you've got a big turnout and not a big turnout, and then it might not rain, but you might have a big turnout and not a big turnout. So you've got a big turnout, not a big turnout, a big turnout, not a big turnout. On a rainy day, the probability of a big turnout is 0.4, which means that must be 0.6. But if it doesn't rain, the probability of big turnout increases to 0.9, and that's 0.1. Now in terms of notation, this 0.4 here, for example, is the probability that there is a big turnout given that it rains. So that's what that 0.4 is representing in terms of notation. The probability that there's a big turnout given that it rains. This is the probability that there's not a big turnout given that it rains. This is the probability that there's a big turnout given that it doesn't rain. and this is the probability that there's not a big turnout given that it doesn't rain. Okay, so that's just the notation. To answer the questions, we're just going to go through the usual routine. Probability that there's a big turnout and it rains. So the probability in symbols that there is a big turnout and it rains, well, that's the probability of it raining, which is 0.75, times by the probability of a big turnout, which is 0.4, which altogether is 0.3. Okay, and you can see here that that's 0.75, that's the probability of it raining, and that's 0.4 is the probability of a big turnout given that it rained. Okay, so you can see here the appearance or the use of that multiplication rule, but without really thinking of it as the multiplication rule. So when you've been doing tree diagrams this whole time, in effect you've been using the multiplication rule without really realising. So that's part B. Part C, the probability of a big turnout. So it's either going to be that, or it's going to be that and that. So it's the previous answer plus not rain times big turnout. So plus 0.25 times 0.9, which is, for some reason I've not worked it out, plus 0.25 times 0.9, 0.525. Okay, so in terms of actual working out all the answers, you would have known how to do that before any of this information, but it was just so that you could see the link between what you've been doing previously in terms of the multiplication rule and how that worked on a tree diagram. Okay, next one, all we've got is a load of symbols, so this is where you do need to understand what this means. Probability of A is 0.63, probability of B given A is 0.8, probability of B given not A is 0.35. Okay, this is showing that B is dependent on A and not A happening. Therefore, if we want to draw our tree diagram, then A is going to have to come first, and then after that we can put on the B's. So we've got A, not A, and then we've got B, not B, B, not B. So that's 0.63. That's going to be 0.37. So this, the probability here, is going to be the probability of B given A, which is going to be the 0.8, which means that's 0.2. And then this probability is going to be the probability of B given not A, so that's where the 0.35 goes, which means that's 0.65. Okay, so now we can work out from the tree, probability of A intersect B. Well, the probability of A intersect B is the probability of A times the probability of B given A. So A intercept B is going to be 0.63 times 0.8 which is 0.504. B, not A intercept not B, so that's going to be the 0.37 times by 0.65. So that's the probability of not A times by the probability of not B given not A. So it's the probability of not A times by the probability of not B given not A. So it's going to be 0.37 times by 0.65, which is 0.2405. C, probability of B. Well, the probability of B is going to be A and B, A intercept B, plus not A intercept B. So it's our previous answer, which was the 0.504. So that's that, plus not A and B. So plus 0.37 times by 0.35, which is 0.6335. Now then, probability of A given B. B is dependent on A, but this one is asking for A given B occurs. So this is really difficult to get from the tree diagram. So what I would do here is I would use my multiplication rule. We know that this is true, but we also know we can rearrange it and say that if that was B, then that'd be A given B. So this is the probability of A intercept B divided by the probability of B. The intercept is that times that, therefore A given B is that divided by that. Well, we've worked those two bits out. A intercept B, that's what we had from the start. So that's 0.504. And we need to divide that by the probability of B, which we've just worked out, which is 0.6335. And that gives 0.7956. So once you've got to a certain point with your tree, at some point they might ask you a question that requires you then dipping into the multiplication rule. And then for E, we want A or B. Again, the easiest thing to do here now is to work out, use the addition rule, because we know what that is. We're told that at the start. We've worked out what that is, and we know what the intercept is. So for the union, probability of A is 0.63 plus the probability of B, which is 0.6335, take away the intercept, 0.504, and that gives an answer for the union of 0.7595. Okay, so we've started off by using the tree and then eventually was forced to do some formulae. An alternative approach, once you've got this, and possibly this, you could then start putting things on a Venn diagram. Okay, because once you've got this and this and this, you could then just draw a Venn diagram and then work those out based on that, the Venn diagram. So again, it's a matter of what you prefer to do. Do you prefer formulae? Do you want to draw a Venn diagram? As soon as you can draw a Venn diagram, if you want to, draw one. Okay. Right, last one. Sue's got 2 coins. One is fair, with a head on one side and a tail on the other. The second is a trick coin and has a tail on both sides. Sue picks up one of the coins at random and flips it. Find the probability that it lands heads up, and then given that it lands tails up, find the probability that she picks up the fair coin. Okay, so it's a bit of a funny question really, because it's not obvious straight away how to start. But there are 2 things happening. First of all, she picks up a coin at random. So that's the first thing that she does. So the first branch is going to be her choice of coin. So is it a fair coin or is it not a fair coin? Okay, there's 2 coins, one of them's fair and one's not fair, which means that each one of those is a half. The second thing she does is she flips it. If it's a fair coin, then there are 2 outcomes. There's a head and a tail, or head and not a head, or head and tail. If it's not a fair coin, well, there's only one outcome, so I'm only going to draw one branch, and it's a tail. If it's a fair coin, that's a half, and that's a half. And if it's not the fair coin, then you're only going to get tails, so that must be 1. So it's a bit of a funny looking tree. So find the probability that it lands heads up. Well, it's only going to land head up if it's the fair coin and it lands on heads. So the probability that it's going to land on heads is going to be a half times a half, which is a quarter. Given that it lands tails up, find the probability she picks up the fair coin. Okay, so in symbols, given that it lands tails up, find the probability she picks up the fair coin. We can write that as the probability that she picked up the fair coin given that it landed tails up. Okay. The easiest thing to do here is to use the formula. It's going to be the probability that it's fair and land tails up divided by the probability that it lands tails up. Okay, so fair and lands tails up, so that's going to be a half times a half, which is a quarter, and the probability that it lands tails up, well, if it lands heads up, it's a quarter, which means it's going to land tails up 3/4. So 1/4 divided by 3/4 is going to be a third. Okay, so again, I resorted in using the formula to work out that given. Right, there's 2 questions to do. One's to do with Bill and his travels, and one's to do with blue balls and green balls. So what I would like you to do, so there's the first question, there's the second question. What I would like you to do is pause the video, have a go at both of those questions in the booklet, and then I will go through it. Okay, so you should have now had a go at the questions. So Bill travels to work by car, bus or train. And then the probabilities of being late based on that. So being late is dependent on his travels. So he's got car, bus and train. And then he's got late, not late, late, not late, late, not late. So we've got car, bus, train, late, not late, late, not late, late, not late. So that's 0.1, that's 0.6, that's 0.3, 0.55, 0.45, 0.3, 0.7, 0.05, 0.95. Okay, so there's the tree diagram to represent that information. Find the probability that on a randomly chosen day, Bill travels by train and is late. So the probability that he travels by train and is late is going to be 0.3 times 0.05, which is 0.015. Probability is late, so it's going to be that, train and late, so he's either going to get the train and he's late, or he's going to get the car and he's late, or he's going to go on the bus and is late. So that should be 0.25. And then C, given that Bill is late, find the probability that he did not travel by car. So the probability that he didn't travel by car, given that he's late. Again, if we use the formula, that's the probability that he didn't travel by car and is late, divided by the probability that he is late. Okay, so use the formula. If he didn't travel by car and is late, well, that's bus and is late, train and is late. So it's 0.6 times 0.3. That's the bus and is late. Or he could have travelled by the train and was late. And that's divided by the probability is late, which you worked out in that last part of the question. So all of that divided by 0.25 is 0.78. Okay, so again, draw your tree, get what you can off your tree, and then if need be, for the given question, use the formula. And then the second question, bag contains 4 blue, 7 green, but then we've got no replacement. So blue, green, blue, green, blue, green. I'm just going to use some subscripts here actually. So the first one's blue or the first one's green, the second one's blue, the second one's green, the second one's blue, the second one's green. Just so you can see what we're talking about first or second, because it refers to it in the question. So that's going to be 4 11ths and 7 11ths, 3 10ths 7/10, 4/10, 6/10. Find the probability that the second ball selected is green. So the probability that the second ball is green, so it's going to be either the first one's green and the first one's blue and the second one's green, or it's going to be the first one's green and the second one's green. So either the first one's blue and the second one's green, or it's the first one's green and the second one is green. So 28 plus 42, 28 plus 42, 70 110ths, or 7/11ths. And then C, both balls selected are green, given that the second ball selected is green. So the probability that both balls are green, given that the second one is green. So this is a bit of a funny one, because technically we need to use the formula. So it's going to be the probability that both balls are green and the second one is green. So it's sort of that. So I'm not going to do another one because that is sort of within that, divided by the second one is green. So the probability that both ones are green is 7/11ths times 6/10ths divided by the second one is green, which is 7/11ths, which is 6/10ths, which if you think about it, is just going to be that. Okay, so it was a bit of a weird one, that one. Okay, practice. There are some more tree diagrams that are worth practicing, especially for all those given questions that get a bit complicated at the end. So exercise 2E, page 31, and that's the end of this video.